aspect ratio on the behavior of rigid water storage tanks. I noticed that we might have a wide assortment of attendees. Therefore, what I'm trying to do, or what I will try to do, is to do it in a colloquial manner and away from hardcore technical problems, so that everybody will be able to follow what I'm talking about. And I start by explaining what is aspect ratio. Aspect ratio means it's the height over the width. If we have a cylinder, then the aspect ratio of the cylinder is the height of the cylinder divided by the diameter of that cylinder. And because I am talking to you from the Holy Land, and also because we are talking about water storage, I thought it would be good idea if I present to you a glimpse of the Holy Land and about water storage facilities that existed in biblical times. Probably those storage tank facilities existed were the first in the world, the first in history that existed in the history of mankind. And they are called the King Solomon pools. For those of you who know a little bit at least about the Old Testament, about the Bible, then they would know the story of King David and his son King Solomon. Those are three water tanks that were used to store water. And from those tanks, water was channeled to Jerusalem. I have three pictures here that explain what I'm talking about. And I should tell you that there is a lot of engineering went into the design of those tanks. They are not at the same level. One tank is higher than the bottom of the next one, and so on and so forth. The capacity, they are carved in rock, partly built of masonry and buttresses. They were built by King Solomon. King Solomon is the son of David. And in the year 50 before Christ, Herod the Great supplied Jerusalem by drawing water from those tanks, from those pools, we call them pools, from Bethlehem. Those pools, by the way, they are situated in the city or south of the city of Bethlehem. Bethlehem is the place where Jesus was born. And through a system of aqueducts and gravity, Herod was able to draw water from those pools to supply his palace with water and also the city of Jerusalem. The capacity of those pools is a whopping 300,000 cubic meters. There also I want to add a little bit more information for those who know the Bible and they know the book. They know about the book of Song of Songs. The Song of Songs was written by Solomon, in what we call Hortus Conclusus, in that area. That area was a very beautiful, had a very beautiful landscape, and still now is a very beautiful place to visit, beautiful place to live in. And this is where Solomon was living, and this is where he wrote the book of Song of Songs. I thought that this would be a good introduction to the subject of today. Water storage tanks are pivotal in any bulk water carrying system. Water storage, again, as I just said earlier, it is a null concept. Nothing is new here. Usually, the location and the land availability dictate the topology of the land of the text. Why? Because sometimes people have to build shallow and stubby tanks. Sometimes they make them deep and slender if we talk about the same capacity. So which way do we go? Which way is forward? Do we go for a shallow and stubby one, or do we go for a deep and slender one? This is usually a question posed by engineers on site and also by engineers that are at the drawing board and they want to design. I always say that land availability is the primary factor that decides, but again, uh, designers have to know the impact of the what I call the 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 aspect ratio on the design. And again, due to various reasons, at least in this area, because this country here lies on an active seismic zone. Seismic design of major importance. Static loadings on tanks is really trivial. No, what I mean, it's important, but not as important as seismic loadings. So here in this study, what I try to do is to evaluate and compare design forces so that I may come up, at least hope to come up with a recommendation of to tell people whether to go for a slender tank or a short and chubby. In the analysis and the design, I refer to American codes because they are accepted worldwide and also adapted in this country here where I live. When when water is in any container and the earthquake happens, the water starts vibrating. Just imagine yourself holding a cup of tea or coffee and running upstairs. You will see how the coffee moves in the cup as you move. Usually, water is divided into two components. One is the component of what we call impulsive, and one is the convective. Again, I don't want to spend too much time talking about them, but I can tell you that the surface of the water behaves differently than the bottom of the water. And this is it. We have surface effects, and we have the water that is at the bottom. A lot of studies have been made on such things, and so that people will be able to say this is too much. This slide is too much mathematics, and I don't want to talk about it because I want to respect everyone that is in the audience, and this is highly technical. It is not of interest to many people. But I can say that the loadings on tanks usually are inertial forces due to the acceleration. You have hydrostatic forces, which is usually triangular, zero at the top of the surface, maximum at the bottom. And then we have hydrodynamic forces that happen due to the separation of surface effects from the rest of the body of water. At times, we worry about vertical ground acceleration, but this is really highly technical, and we don't need to worry about it during this presentation. The tanks that I I'm talking about are cylindrical. They can come in various shapes and forms, but for the sake of the present discussion, I selected a cylindrical, rigid, ground supported. When I talk about rigid tank, I mean it is made of reinforced concrete, but it doesn't always have to be reinforced concrete. Most oil tanks in tank farms use steel tanks, but steel tanks are like a horse of a different color. They behave completely different than a rigid tank. So here we are confined with with reinforced concrete tanks. I selected three tanks. One has a diameter of 20 meters, and one 17 meters, and the other is 12 meters, about 12 meters. And of course, for those interested, they can refer to the paper where all the details are spelled out in detail. Usually, the exercise starts by separating impulsive and the convective, meaning the surface effects from the rest of the body. Then there are tanks parameters again that are well spelled in the code. And we evaluate the forces. Then once we evaluate the forces, we apply them on a computer model and carry out the detailed analysis. In this paper, I did not do numerical modeling. I did not apply it on an actual model because I wanted to make the presentation and also the paper as less technical as possible using hand calculation. Because if we want to go to numerical methods, then it will be we will get into the zone which I call complicated zone, and it will not be of interest to the majority of those people present. I can tell you from this slide, the one at the left hand side, we can see that the impulsive component is in for a shallow tank, the impulsive component is predominant, while in a deep tank, the convective component is predominant. Meaning what? Meaning the surface effects are more pronounced in a deep tank. And again, here it shows in this slide, we show how forces are applied. They take this trapezoidal shape. The shape is the same in both tanks, but the values are different. However, for the convective, notice that for a deep tank, the force is almost zero at the bottom, while for the shallow tank, there is force at the bottom. And this is really, for those people who are interested, they will see that in the deep tank, the convective part is really the predominant one. Here in this slide, I showed that we talked about inertia forces. Inertia forces of the roof, because it is a deeper tank, then the effect of the roof, the inertia of the roof, again, is more pronounced in the deep tank, as it is shown on the left side of the slide. Here we talk about centers of gravity. Centers of gravity, because when we want to compute bending moments, bending moment is defined as a force times distance. So when either a force is large or the distance is large, one of them is large means that the multiplication will be large, which means that the bending moment would be large. Here we choose the it's in this slide we show the lever arm, for the deep tank and for the shallow tank. We notice that here in this slide here, we can notice that the distances are larger for a deep tank and also for the convective part. Now, in this slide here, we talk about sloshing. What is sloshing? Sloshing is the height of the wave that is created when a tank moves. To help you understand this, imagine yourself holding a cup of coffee and walking, and in the same instant, imagine yourself carrying a tray full of water and walking. You will notice that it is very difficult to walk if you walk with a tray full of water, and it is rather easy to walk with a cup of coffee. The reason here is the sloshing height. The height of the wave that's created. We notice that for a deep tank, the wave height is higher than that of a shallow tank, which means what? It means that the freeboard, because in tank we don't fill tanks to the rim. We have to leave part of the tank empty so that when water moves, it will not carry with it the roof of the tank and creates a disaster that no one wants. And this space that we leave empty is what we call freeboard. The freeboard in a deep tank has to be higher than that in a shallow tank, which means what? It also means that the lever arms that we talked about before will be larger also, which will end up with having a bigger bending moment at the base of the tank. So from here, we come to the conclusion. The conclusion says that in a shallow tank, the impulsive component is more than the convective. In a deep tank, the convective is more than the impulsive. The third one, which I just talked about, the freeboard must be bigger in deeper tanks. Hence, we will have larger moment arms. All this means that the wall thickness in the deep tank is thicker than that in a shallow tank because forces will be more. I mentioned earlier that the convective pressure vanishes at the deep tank, and this is good because we don't want it there to be there, but it means that the convective pressure is more at the surface effect. And by the way, these surface effects you can notice it anywhere, even in oceans, even in sea, and when swimming pool. You see that the water perturbates the surface. The water at the surface perturbates. At the bottom, one feels nothing. And again, we talk about base shear. Base shear, again, this is a technical term that can only be appreciated by structural engineers. And it says that base shear is larger in magnitude in deep tanks. Again, hoop stresses are less in deep and stubby tanks. What does it mean? It means, in a nutshell, short and stubby tanks enjoy the edge. Meaning, if I were to select, if everything is the same and somebody asks me, what do you recommend? Which way is forward? What tank would you like us to design? Do you want us to design a short and stubby or long and slender? I would go for a short and stubby tank because it sustains smaller design forces and this is it, smaller sloshing height. This sloshing height is very, very, very important, because anything that goes wrong, if the sloshing height is less than is required, then the water tends to carry the roof upward and cause a disaster, construction disaster that again nobody wants. And again, when we talk about reduced wall thickness, we talk about less material, less steel reinforcing bars, uh, less concrete. Meaning what? Less money, less cost. Of course, again, we talk about the same, if we talk about the same capacity. For the same capacity, we will have less wall thickness, less rebars, reinforcing bars, smaller sloshing height, less design forces, and therefore we go for the short and stubby. And again, at this time, by the way, we are here in at the threshold of the Passion Week, meaning the week of Easter. Tomorrow is Palm Sunday here in Jerusalem. And you know, when Jesus entered the city triumphant as a king, and then the Passion Week follows right afterward, the following Sunday will be Easter Sunday. So I think it is only proper for me to wish each and every one of you, of the audience, peace on earth from the old city of Jerusalem. This is where it all happened. This is the message of Jesus. This is where it all started. And I thank you all for your very kind attention.